Okay, students, so we are now on lecture 21, and I was teaching you previously till lecture 20 a bit of what is called igneous petrology, phase diagrams. We had done 2 phase diagrams. In fact, 2 phase diagrams I had done in the class. One was eutectic system, and the other one was a solid solution binary, and I asked you to read up what is called the peritectic relation or incongruent melting relation, and a binary phase diagram based on that relation. I think by this time now you have understood that it has to be phosphorite quartz, which is one of the most famous and well-known phase diagrams that are discussed in almost all books throughout the internet. But I suggested 2 books from where you will get very good reading. I hope you have done it. Now we need to sort of try and conclude or close off the igneous petrology part, but I will need a little more time. In the meantime, I'd send you 3 PDFs, one PDF with 3 pages. The first page had a classification of minerals. The second page had the famous what is called Bowen's reaction series. And the third one is the name of the rocks that formed due to magmatic processes. Now, you have a full course in crystallography and mineralogy that is running parallel to this course, but I don't know at which part you are. So far, I have tried to avoid naming minerals because I thought it would be a little bit of strain on you. So I have tried to avoid it, and I've written it A, B, C, wherever it is possible, trying to avoid the name of minerals because some of them become quite cumbersome. But I think I have now reached a point where I can't avoid them anymore, because now I come to rocks, and rocks are formed of minerals, and you should know the minerals before you know the rocks. So I have come to this very difficult task of telling you very, very briefly about a very, very small number of minerals which would serve my purpose. But I can tell you there are hundreds and thousands of minerals, and a lot can be said. In fact, when I was a student like you, as a 5-year integrated student, we had a full-scale mineralogy class. We had a full mineralogy course of 1 semester. Nowadays, of course, it has been compressed. We had 1 course on crystallography, 1 course on optical mineralogy, and 1 course on mineralogy. These 3 courses are now clumped into one, which I think Professor Bowman teaches you. So, but now I have to put in a little bit of my effort into it so that I can talk about rocks, and if you have to talk about rocks, you should know the minerals. So I have to, but I will try to keep it as tight as possible so that I just give you the very brief idea of minerals. If I just name the minerals, then you don't get a hang of it. So I have to put the minerals in a perspective. Now, one of the perspective of is, you must have already known now, crystallographic systems. These are systems, crystallographic systems are where crystals form with diverse geometries, but many of them can be classified into 7 crystal systems, which you all know now. Starts from the cubic system, then you have the tetragonal system, you have the hexagonal system, you have the trigonal system, you have the orthorhombic system, you have the monoclinic system, and you have the triclinic system. These essentially are the outer manifestation of the crystals as you see. So these are essentially dealing with the manifestations that is called the morphology of the crystal. The crystal morphology is based on that. But mineralogy essentially deals with the internal structure of the mineral and bonding characteristics, where are elements placed, etc. These are more very, very complicated situations, and you cannot understand it very much without 3-dimensional images and turning it around, you don't get the hang of it. It's the internal. When mineralogy tells you a little bit about the internal structure and composition of a mineral, crystallography essentially tells you the outer part of it, the morphological part of it. So now I will try to combine both of it into some small of us, say a nutshell, into which to introduce you to minerals. So I have with me the page, you can see with my notes, the page on which I gave you, your first page. So this lecture 21 is essentially a clarification or amplification of the first page of the PDF. Now it is important that the main building block, as I have told you before, the main building block of a silicate mineral is the SiO4 tetrahedron. Is essentially the SiO4 tetrahedra, where you have 4 oxygen atoms around it, 4 oxygen atoms, and inside you have a silicon atom. Inside you have a silicon atom which has 4 positive charges, and they are balanced by oxygen with 2 negative charges. So essentially you have 4 positive charges and 8 negative charges. So the SiO4 tetrahedra is SiO4 4 minus. This we have talked a little bit about it. Now what I did not tell you is this SiO4 tetrahedra, the internal mineralogy, internal structure of the SiO4 tetrahedra, the internal structure of mineral is built on an arrangement of this SiO4 tetrahedra. So essentially, say for example, if you have an isolated SiO4 tetrahedra, or for example, you can have a structure whereby you have an SiO4 tetrahedra that is shared. So here, for example, when it is an isolated tetrahedra, and this is a shared tetrahedra, you can see this has a charge of 4 minus, and the formula is SiO4. Here, you can see that there are 2 silicon atoms. There are 2 silicon atoms right here and right here, and there are 1, 2, 3, 4, 5, 6, and 7 oxygen atoms when you have a shared tetrahedra. And you can see it's Si2O7, 14 minus, 8 plus, 6 minus. Similarly, you can have a tetrahedra which is arranged in the form of a triangle. So you can see they are formed in a triangle. So here you have 3 silicon atoms. Here there are 3 silicon atoms. But you can count the number of oxygen atoms. So you can have isolated tetrahedron, you can have shared tetrahedron, and you can have cyclical tetrahedron, you can have a chain of tetrahedron, and you can have a 3-dimensional network of SiO4 tetrahedron. You know, for example, very clearly, sp2 and sp3 orbitals. So you know it's a structure. Essentially, it's a structure. So what has happened is, in mineralogy, this SiO4 tetrahedra can be arranged in different formats. And based on that, silicate minerals are divided into the forms that I have told you. It will be better if you can keep the PDF in front of you so that I don't have to always refer to it. So you can have silicate minerals which are named differently. Say, for example, you can start with nesosilicates. Nesosilicates. These are isolated tetrahedra. I am not writing it. because I have already sent you the PDF. Then we have sorosilicates. Then we have cyclosilicates. Then you have ionosilicates. These are actually called chain silicates. And you can have single chain, these, and you have double chain silicates. And then you have phyllosilicates, PHYLLO. You can see the arrangement in the PDF that I have given. These are some of the important silicates. Then you have, of course, the tectosilicates, the very famous tectosilicates. Tectosilicates. Now, always, all minerals are three-dimensional in nature. Three-dimensional in nature. But every mineral structure has a particular arrangement of SiO4 tetrahedra. And if you have that particular unit, this is called unit cell. Unit cell. These are called unit cells. The unit cells have particular length, breadth and height. They have the symmetry elements. So if you shift the unit cell laterally, that orientation of the unit cell is uniform throughout a particular single crystal. Have you understood? So that's what unit cells are called, crystal lattice. These are called crystal lattice. So and another thing is that every unit cell has a particular, it's electrically neutral. So it's essentially that particular volume with those characteristics. If you move laterally and shift it or tangentially without rotating it, and then you will be able to generate the crystal. So that particular unit cell also has a volume. Say, for example, if you have an isometric system which is formed of a cube, for example, isometric system. You know the isometric system, I hope, that you have. You know, it has the characteristic of an isometric system is all the axes are of equal lengths. And all the angles between the axes, say for example alpha, beta, gamma, they're all equal to 90 degrees. So you have, for isometric system, you have all the three crystallographic axes that are equal in length, and the angles between them are all 90 degree. Angles between the axis, inter-axis angles are all 90 degree. But say for example in the tetragonal system, you know, the two horizontal axes are different, which are called two horizontal axes are same, they are called A and A, but the vertical axis is called C because that is the different, has a different length. So in the tetragonal system, you have A1 is equal to A2 is not equal to C. C is the vertical angle, so A1 is equal to A2, but is not equal to C. But all the angles, alpha, beta, gamma, between the three axes, you know it now, alpha, beta, gamma, the angles all are 90 degrees. But say for example the triclinic system, if you go that way, then you have the isometric system, you have the tetragonal system, you have the orthorhombic system, you have a hexagonal system, you have a trigonal system, you have a monoclinic system, and you have a triclinic system. So you have different systems, minerals of these different arrangements of SiO4 tetrahedra belong to 7 crystal systems in all. And 32 classes, I'm sure your teacher must have derived the 32 classes, but what is important is there are 7 crystal systems, and all these minerals with diverse linkages of the SiO2 tetrahedra fall into 7 crystal systems and 32 crystal classes. Right? And remember this very important unit, this unit is called unit cell. And the unit cell obviously has a volume. So let me write the volumes here. For unit cell volume, it is calculated, the repeat unit cell volume for the isometric system, where all the three axes are the same and the angles are 90 degrees. It's called acute. That's the unit cell volume for acute. And then you have the tetragonal system. Which is essentially A square into C. And then you have the orthorhombic system, for which the unit cell volume is A into B into C. That's the orthorhombic system. And then you have the hexagonal system, tetragonal, trigonal, and the hexagonal system, where the unit cell volumes are A square C sine 60 degree. That's the unit cell volume. You can find this geometrically. Then you have the monoclinic system. It's ABC sine beta. And then you have the very, very long formula for triclinic system. Unit cell volume, triclinic system. This is ABC into 1 minus cos square alpha minus cos square beta minus cos square gamma and plus 2 into cos alpha, cos beta and cos gamma, and this is raised to the power half. So that is the unit cell volume for a triclinic system. So essentially what I am trying to tell you is that SiO4 tetra is the building block of a mineral. The SiO4 tetrahedra can be arranged as a single tetrahedra. It can be a shared double tetrahedra. It can be a tetrahedra linking 3 tetrahedras. You can have linking 6 tetrahedras. You can have chains of tetrahedras, single chain tetrahedras, double chain tetrahedras, and you can have also phyllosilicate, which are essentially called sheet silicates. These are called sheet silicates. They occur in clines, a planar arrangement of a SiO4 tetrahedra, and they have characteristic composite and they have characteristic charges. I don't go into this. I have given it here. You can read it, and there are many, many sources when you can read it, even for the internet or from books. These are all given everywhere, and your teacher will teach you later on. And then you have the unit cell volume, which is essentially the volume consuming smallest unit, which can be translated, and you will get the whole mineral structure, and that is called the unit cell. And the unit cell volumes are calculated as I have given here from the lengths of the crystallographic axis ABC or A1, A2, A3, and the interaxial angles, which is alpha, beta, gamma. So it can be found out, the unit cell volumes can be found out. For our case, we will talk of only a few minerals. I will try to keep it as few as possible because some of the names are a little complex and you might have a little difficulty in remembering them, but there is no alternative. You have to remember them. Only very, very basic minerals, I will tell you. Without this, we can't proceed. Without this, we can't proceed to anything to do with introduction to earth science. So long I've been hiding it, but I can't hide it anymore. I will let it go. So the minerals that are important here, you have to write it down. I will tell you a little bit. Olivine and garnet. Olivine and garnet. These are two important minerals. I'm not giving you all. Then there is a mineral called orthopyroxene and clinopyroxene. And there is another mineral called amphibole It's a very complex mineral. I don't want to go into the details of it. Or sometimes in some books you might read it as hornblende. You may read it as hornblende. There are differences between amphibole and hornblende, but for our case, we are at the very introductory level. We will keep it simple. We will keep amphibole or hornblende, but essentially there is a major difference. But we will talk, say, amphiboles or hornblendes. And then we have another mineral, muscovite. Muscovite, and a mineral called biotite. And then you have three minerals which are very important: quartz, orthoclase, and plagioclase. These are some of the minerals you have to remember. There is, I find, no alternative but that you have to remember that. When your teacher teaches you in mineralogy, he will teach you many more. He can do it, but I have to go on with my course, and I will try to just leave it to the minimum of it so that you remember. Now, importantly, garnet, you should remember this, garnet crystallizes in the isometric system. You must remember this. Garnet is in the isometric system. Olivine, this forms in the orthorhombic system. Orthorhombic system. Orthopyroxene is an inosilicate. Orthopyroxene is in the orthorhombic system. Orthorhombic system. Clinopyroxene is in the monoclinic system. Amphibole and hornblende, this is also in the monoclinic system. Muscovite and biotite, these are also in the monoclinic system. Quartz, this is in the trigonal system. And orthoclase and plagioclase, this is in the monoclinic system, and plagioclase is in the triclinic system. So these minerals crystallize, and these are required for what I am teaching. There are other minerals, but by that time I think your teacher in mineralogy will have told you. So that will be required at a later stage. Important here is olivine in the orthorhombic system, garnet is in the isometric system, orthopyroxene is in the orthorhombic system, clinopyroxene monoclinic system, amphibole monoclinic system, muscovite monoclinic system, biotite also monoclinic system, quartz in the trigonal system, orthoclase in the monoclinic system, and plagioclase in the triclinic system. Having said this about the SiO4 tetrahedron, I have to tell you a little bit. So olivine is a nesosilicate. Nesosilicate. This is nesosilicate means independent SiO4 tetrahedron. Arrangement block, the main block repeat unit is something to do with SiO4 tetrahedron. Then, for example, garnet is also a nesosilicate. Here, in both the cases, the basic unit is Si4 4-. The basic building block is SiO4 4-. The orthopyroxene is an inosilicate. Inosilicate. So is clinopyroxene, which is inosilicate. Here the basic building block is Si2O6. So you can see it's 4 minus again. Si2O6 is the building block. Amphibole is much more complex. This is also inosilicates. And the formula for amphibole is Si4O11. Si4O11 6 minus. That's how the amphibole looks like. Muscovite and biotite, both of them, I know muscovite and biotite, both of them are phyllosilicates. Phyllosilicate. And the basic building block of this is Si2O5 2 minus, Si2O5 2 minus. Then we have the trigonal system quartz. These are all pectosilicates. Pectosilicates. So these are all pectosilicates, and the formula for this is SiO4 4 minus. You could say that why isn't this here? Because the structure of this and the structure of this are very different. Although the basic unit, the unit cell volume has a 4 minus, has a basic structure is SiO4 4 minus, but there's a large difference between the arrangement of silicon and oxygen here and between this and this. So you have to remember this. This is the most important part. These are the crystal. These are the classification, mineralogical classification of silicates in the blue. Mineralogical classification. So it talks about the internal structure of the mineral, whereas this one, for example, is the crystal system in which they crystallize normally, and this gives you an idea of the external morphology. I must tell you that the external morphology and the internal mineralogy have great linkage. It's not arbitrary. It has tremendous linkages, that if you have this type of arrangement, this would be the morphology. But what happens in when mineral grows, sometimes its growth is related to diverse factors, and so they grow to develop shapes. But overall, the internal mineralogy and the external morphology, they are related. They are not independent of each other, they are related. But these are the minerals at least you should remember for my class. Yeah, I'm sure that your teacher in metamorphic crystallography and mineralogy will have the time to talk of details about it. But as for me, I will have not more time, so I have sort of condensed it, and this is it. Now, given this, I will now tell you a little about the compositions of these minerals. Remember, we now know that what is solid solution, etc., all this we know, so we will talk about the compositions. And again, I will talk about the compositions in a very brief way, not in a great depth, so that it's just about adequate for you to know what the mineral looks like. So for example, here the mineral quartz. You know that it crystallizes in the trigonal system. It's a tectosilicate, which is a three-dimensional arrangement of SiO4 tetrahedra, and that it crystallizes the trigonic system, but you don't know what is the composition of it. So I will tell you briefly the compositions of these minerals so that you understand a little bit of what I will be talking about. If I don't tell you, you will not know what I've been talking about. Right? So, I will erase this part. I will try to be as brief as possible so that you feel comfortable. Now, olivine, this mineral I have talked to you, it has, the formula is MgFe whole twice SiO4. MgFe whole twice SiO4. This is the composition of the mineral. Again, I'm telling you, this is just for you. It takes in other elements also, but we don't go into that. This is the building block, SiO4 4 minus. Remember, it's an nesosilicate. SiO4 4 minus has 4 negative charges. You see, you have magnesium 2 plus and Fe2 plus. 4 of them neutralizes the 4 oxygen atoms, so now it's electrically neutral. So olivine, this formula, this is called the mineral phase, and it's formed of what is called Mg2SiO4 and Fe2SiO4. Now, Mg2SiO4 is called forsterite. The name of the mineral is forsterite, and Fe2SiO4 is called firelite. So, forsterite and firelite are two components of the mineral olivine. So what happens? You can mix them as a chemical compound and you can find out the whole range of compositions of olivine. So olivine has MgFe whole twice SiO4. It has two components, Mg2SiO4 and Fe2SiO4. Mg2SiO4 is called forsterite, Fe2SiO4 is called firelite. Now we take in the other mineral, garnet. The general form of this reaction is Ca, again I have simplified it, CaMgFe whole thrice Al2 Si3 O12. That's what is the formula of a garnet. Again you see, Si3O12 means silicon is to oxygen is 1:4. This is a characteristic of a nesosilicate. And it crystallizes in the cubic system, but there are more complications as you can see. So this mineral having this composition is called a garnet, and it is an end member of 3 components. What is it? Ca3 Al2 Si3 O12, Mg3 Al2 Si3 O12, and Fe3 Al2 Si3 O12. These are the 3 components of the solid solution which forms a garnet. Now the names, this is called almandine. The iron end member is called almandine. The magnesium end member here is called pyrope. You have to remember this. It's called pyrope. And this end member, calcium, is called grossular. It's called grossular. So essentially, garnet is a solid solution in a very simple situation as grossular, pyrope, and almandine. There are other components which I have not told you about. It's not necessary for you to know it. But this is how garnet composition looks like. It's a very dense mineral, but all that your teacher in crystallography and mineralogy should be telling you. Then you have orthopyroxene. Here the basic building block is, the formula is Mg, Fe whole twice Si2O6. Now see here, there's an important difference. Here silicon is to oxygen is 1:3, which is a characteristic of single chain inosilicate. Single chain CHIN chain inosilicate. It's a very characteristic. So if you see, you have 8 positive charges here and 12 negative charges here. So it's -4. This is balanced by magnesium and iron. And it has 2 end members, and this is called Mg2 Si2O6 and Fe2 Si2O6. this is called enstatite, and this is called ferrocellite. This is called enstatite and this is called ferrocellite. And see here, almost the name is given. Orthopyroxene means in the orthorhombic system it crystallizes. Again, this is a simplified formula. So your MgFe whole twice Si2O6. First, this is the formula of the mineral, and these are the two components, the end member components that make solid solution of it, makes orthopyroxene. If you take clinopyroxene, I will discuss it in the same way. Clino, this stands for monoclinic. It has a monoclinic symmetry. I have written it before. It has a monoclinic. Monoclinic system of crystallographic system. So it crystallizes a monoclinic system, and the formula is Ca Mg, Fe Si2O6. Now you see Si2O6 is the same here. Only thing here, there are two sites where MgFe was, but now it's been split up, where one is MgFe still and the other is filled up by aluminum calcium. You can ask me why. You have to wait till your teacher tells you why calcium, why this orthorhombic system becomes a monoclinic system. It is because once you have the calcium ion, it is very large. The position of that site has to be shifted in such a way so that the AC angle, beta is the angle between the A and the C axis. So that beta angle is no more 90 degrees, but to accommodate the change, it has to move up from 90 degrees, and that is why it's called. That's why it has a monoclinic system. The details of it, your teacher will tell you. And there are two end members again: CaMg Si2O6 and CaFe Si2O6, and this mineral is called dioxide, and this CaFe SiO2, this is called Heidelbergite. I'm getting old. Heidelbergite. Now, just for your information, those who are interested, Bergen, the word Bergen, B-R-G-N. Bergen is the German for a hill. Sieben Gebirge means 7 sills. So this word Berg comes from hills. So hills that are formed dominantly of this clinopyroxene, which crystallizes in the monoclinic system. And these are single chain silicates, both of them, orthopyroxene and clinopyroxene, are both single chain silicates, but they have a major structural change because of the entry of calcium. And this causes the AC axis angle to rotate off from 90 degrees. If you take the orthorhombic system, which has ABC of unequal length but all 90 degree angles between the axis angles are all 90 degrees. For clinopyroxene, the A and the C angle is off from 90. That has to be done because of accommodating calcium in the system. So, now we come to this important mineral amphibole. Now, this is very, very complex. I don't think it's necessary for you to know the complexity of it. But I will give you the general formula. It's very complex. But it's not complex if I derive them, but it's a mineral complex to remember. The very simple formula is MgFe7 Si8 O22 OH whole twice. This is the easiest to remember of amphibole. This is the most simplest amphibole. Here you can see Si8O22. That means Si4O11 is the silicon oxygen ratio. So if this is so, then you have 16 positive charges, because 4 into 4 16, and you have 22 negative charges. So you have 22, 16, and then you have OH2. So the whole charges, I think, is 7 minus. Yes, 7, no, this is 6 minus 22 minus 16, 6 minus plus OH 2 minus and 7, 14 minus. So it's all balanced. Side 4, O11, oh no, side 4, O11, this is 12. This is 6 minus, but it's written on the double formula basis. So this should be 12 minus plus 2 minus, that's 14 minus, balanced by magnesium and iron. 7 into 2 is 14 plus. So that's how the formula is. The basic structural formula is Si4O11 with 6 negative charges. For the double formula, you have 12 negative charges plus OH2, 14 negative charges. This is balanced by magnesium iron, 7 into 2, 14 positive charges. So it's electrically neutral. Now this again is divided into two parts. One is called Mg7 Si8 O22 OH whole twice, and here it is Fe7 Si8 O22 OH whole twice. Right? Now this mineral here is called anthophyllite. Anthophyllite. This mineral is called anthophyllite, and this mineral is called grunerite. This mineral is called grunerite. Anthophyllite and grunerite. Grün, by the way, is a German word for green. They have the same Latin connection, but in German, green is called grün. Grunerite is green in color. Anthophyllite, if it's a pure anthophyllite, it's colorless to light gray. You know from your basic chemistry that only when you add the coloring elements, which are the transition elements, the color of the minerals change. So if you have more and more iron into anthophyllite, the color of the anthophyllite, which is colorless to first order, first gray in color, would become green in color. So the shade of it is indicative of magnesium by iron ratio. Iron, cobalt, nickel, all these transition elements imparts the color to the element. So this is a little bit about, quickly about the amphiboles. Then we have muscovite. There's a formula. So the formula is KAl2Al Si3 O10 OH twice. That's the formula of pure muscovite. Here there is a problem. Here, in this, muscovite is a phyllosilicate. So it has Si2O5 is the basic building block. So if I double it, then it should be Si4O10. For a double formula, Si4O10. So if it's Si2O5, then it's 5 oxygen minus 2 minus. So 4 oxygen 10, 16, 4 minus. So 4 minus, here you can see. Now here, one of this silicon is replaced by aluminium. So in this structure, the silicon position is replaced by an aluminium position. So this is AlSi3. If you club it, it's Si4. So this is the basic formula. So it is 4 minus, and then you have 2 minus, 6 minus. So you can see you will have Si2O5, 10, 2 minus, 10. So you have 4 minus, 4 minus, plus OH2 is 2 minus, 6 minus. Some problem? Nothing is solved. So it's KAl2, this is the formula of muscovite. And if you replace aluminium by magnesium, you can see if you replace Al3 plus by iron divalent, then 2Al3 plus will become 3Al2 plus. So if you replace aluminium by magnesium and iron, then it should be 3, and then you have AlSi3 O10 OH whole twice. So because these are, your teacher will tell you These are called trioctahedral micas. Trioctahedral mica. And this is called dioctahedral mica. This is muscovite, Kal2AlSi3O10OH whole twice. If you replace aluminium by magnesium, then you get KMgFe3. So there are 3 octahedral sites. And again, you have the same situation here, Si2O5 and 2 minus. So you have this biotites are trioctahedral micas, muscovite are dioctahedral micas. They are very, very classic structures. But the important point is both of them are monoclinic system, crystallizes in a monoclinic system. And so muscovite is iron magnesium free, muscovite is Kal2Si3, these are all aluminium rich, whereas biotite is magnesium iron rich and not aluminium rich. Now a little bit more about biotite. So I told you the formula was KMgFe3 O10OH whole twice. So you can write KMg3AlSi3 O10OH whole twice and KFe3 AlSi3 O10OH whole twice. So you see, this is essentially a solid solution. Between this, the solid solution is here. So this is mineral, this component is called phlogopite, and this is called anite. So the biotite is the mineral is biotite. The mineral is biotite. It is composed of 2 components. One is called phlogopite and the other one is called anite. You remember, muscovite is Kal2. Muscovite is Kal2AlSi3 O10OH whole twice. So here there is no coloring matter. So muscovite is colorless. It's a colorless flaky mineral, muscovite. If you go to Bihar, those who come from Bihar or Rajasthan or some other places like this, you will see that there is shining small particles lying. Those are actually mica. During this holy time, on the colors, on the powders, they put in this fine material that is muscovite. That is muscovite, colorless white mica. But this one is called black mica because they are colored. But both of them are called micas. This is called muscovite, colorless white mica, and this is called dark or black mica because they are colored micas. Now the other mineral, the mineral that is most common, now we remain with the most common minerals in the crust, quartz, orthoclase, plagioclase. Quartz, the formula is SiO2. That's the formula. It's the simplest of all formulas. The mineral quartz contains SiO2. And then there are 2 types of minerals. Feldspar. One type of feldspar is called orthoclase. And the other type of feldspars are called plagioclase. The formula for orthoclase is KalSi3O8. Now this is the ratio. Here you can see this is 4:2. 4:8. That means if you take all of this as silicon, then this is SiO2. Can you see? This is SiO2. Here also it's SiO2. If you take plagioclase, it's between 2 end members. One is called NaAlSi3O8. Again, AlSi3 within bracket. This is called albite. And then you have CaAl2, Si2. Again, I have a bracket. O8, and this is called anorthite. So this is the mineral plagioclase, which is formed by a solid solution of albite and anorthite. So the formula for plagioclase is Na, bracket, NaCa in the same side, and Al, Si4. In albite, Al is to Si is 1:3. In anorthite, Al is to Si is 1:1, O8. This is the formula for plagioclase. And this is the formula for orthoclase. Have you understood? So these are some of the mineral names that you have to remember. You have to remember the following names. Just for a recap, I can tell you these minerals are the most dominant minerals of the crust. These two are the most dominant minerals of the crust. They are the most dominant minerals. In fact, the more dominant minerals are the feldspars, and the quartz comes later. If you take the whole crust, feldspars are the most dominant minerals, followed by quartz. So essentially, if this is the case, quartz has a formula of SiO2, orthoclase has a formula of KLSi3O8, and plagioclase has this formula. If you take 1, 2, and 3, these formulas, then your crust is dominated by aluminium, silicon, and sodium, potassium, and calcium. That means if you go back to the periodic table, you have aluminium and silicon, that's all right. But the other elements that dominate the crust is potassium and sodium, the alkali elements, calcium, the alkaline earth element. So if you look at the crust, it is dominated by silicon and aluminium, and then by alkaline elements, sodium, potassium, and alkaline earth, like calcium. And other elements come in much smaller abundance. Much smaller abundance. If you look at the crust itself. If you look at the mantle, then it is dominated by these minerals. These are the minerals that dominate the mantle. These are the minerals that dominate the mantle. Olivine, garnet, orthopyroxene, clinopyroxene, all of them, you see, I wrote down the formula. If you go back and see my video lectures, they are all iron magnesium rich. That is why the mantle is heavier than the crust. That is because it is dominated by iron and magnesium. So, most of the elements, minerals here at the top are dominant in the mantle. But the minerals that are in the lower part of this are including muscovite, biotite, all of this dominantly form the crust. So this, if you make a division here, it is a vague division, but if you make a division here, all these elements dominate the crust. All these elements dominate the mantle. There are more elements, but these elements dominate at least the upper part of the mantle. That's why the mantle is much heavier. Although you find many of them in the crust, but that's a different issue. We don't go into that now. It's, I think, you're too young to appreciate it. Okay then, thank you very much. We will start our next lecture soon. Right? Thank you.